managing growing projects with package, crates, and modules. As you write large programs, as you write large programs, organizing your code will become increasingly important. Organizing your code will become increasingly important by grouping related functionality and separating code with distinctive features. We will clarify where to find the code that implements a particular feature and where to go to change how a feature works. You will clarify where to find the code. You will clarify by grouping related functionality and separating code with distinct feature. You will clarify where to find the code that implements a particular feature and where to go to change how the feature works. The programs we've written so far have been in one module in one file. The programs we've written so far have been in one module in one file. As your project grows, you should organize code by splitting it into multiple modules and then multiple files. The programs we've written so far have been in one module. Okay, as your project grows, you should organize code by splitting it. You should organize the code by splitting it into multiple modules and then multiple files. A package can contain multiple binary crates. A package can contain multiple binary crates and optionally one library crate. As a package grows, a package can contain multiple binary crates and optionally one library crate. As your package grows, you can extract parses into separate crates that become external dependencies. You can extract parses into separate crates that become external dependencies. This chapter covers all these techniques. For very large projects comprising a set of interrelated packages that evolve together. For very large projects comprising a set of interrelated packages that evolve together. For very large projects comprising a set of interrelated packages that evolve together. Cargo provides workspaces, which we will cover in the Cargo Workspaces section in Chapter 14. We will also discuss encapsulating implementation details, which lets you reuse code at a higher level. We will also discuss encapsulating implementation details. We will also discuss encapsulating implementation details. Encapsulating implementation details, which lets you reuse code at a higher level. Once you've implemented an operation, other code can call your code via its public interface without having to know how the implementation works. The way you write code defines which parts are public for other code to use and which parts are private implementation details that you reserve the right to change. This is another way to limit the amount of detail you have to keep in your head. The way you write code defines which parts are public for other code to use and which parts are private implementation details that you reserve the right to change. This is another way to limit the amount of detail you have to keep it in your head. A related concept is the scope. A related concept is scope. The nested context in which code is written. The nested context. A related concept is a scope. A related concept is a scope. The nested context in which code is written has a set of names that all are defined as in scope. When reading, writing, and compiling code, programmers and compilers need to know whether a particular name at a particular spot refers to a variable, function, struct, enum, module, constant, or other item, and what that item means. A related concept is a scope. A related concept is scope. The nested context in which code is written has a set of names that are defined in scope. The nested context in which code is written. The nested context in which code is written. The nested context in which code is written has a set of names that are defined as in scope. When reading, writing, and compiling code, programmers and compilers need to know whether a particular name at a particular spot refers to a variable, function, struct, enum, module, constant, or other item, and what that item means. You can create scopes and change which names are in or out of scope. You can not have two items with the same name in the same scope. Tools are available to resolve name conflicts. Rust has a number of features that allow you to manage your code organization. Rust has a number of features that allow you to manage your code organization, including which details are exposed, which details are private, and what names are in each scope in your programs. These features are sometimes collectively referred to as the module system. Package is a cargo feature that lets you build, test, share your crate of tree of modules that produces a library or executable. Tree of modules that produces library or executable. Modules and use let you control the organization, scope, and privacy of passes. Passes a way of naming an item such as struct, function, or module. In this chapter, we will cover all these features, discuss how they interact, and explain how to use them to manage the scope. By the end, you should have a solid understanding of the module system and be able to work with scopes like a pro. We will cover all these features, discuss how they interact, and explain how to use the managed scope. By the end, you should have a solid understanding of module system. Packages and crates. The first parts of the module system we will cover are packages and crates. The first parts of the module system we will cover are packages and crates. The first part of the module we will cover packages and crates. A crate is the smallest amount of code that the Rust compiler considers at a time. Even if you run Rust C rather than Cargo and pass a single source code file, as we did all the way back in the writing and running Rust program section of chapter 1, the compiler considers that file to be a crate. Crates can contain modules, and the modules may be defined in other files that get compiled with the crate, as we will see in the coming sections. A crate can commit one of two forms, a binary crate or a library crate. Binary crates are programs you can compile to an executable that you can run, such as a command line program or a server. Each must have a function called main that defines what happens when the executable runs. All the crates we've created so far have been binary crates. Library crates don't have a main function, and they don't compile to an executable. Instead, they define functionality intended to be shared with multiple projects. For example, the rand crate we used in Chapter 2 provides functionality that generates random numbers. Most of the time, when Rustasians say crate, they mean library crate, and they use a crate interchangeably with the general programming concept of a library. Instead, they define functionality instead to be shared with multiple projects. For example, the rand crate we used in Chapter 2 provides functionality that generates random numbers. Most of the time, when Rustasians say crate, they mean library crate, and they use a crate interchangeably with the general programming concept of a library. For example, the rand crate we used in Chapter 2 provides functionality that generates random numbers. Most the rand crate. Most of the time, when Rustasians say crate, they mean library crate, and they use a crate interchangeably with the general programming concept of a library. Crate can come in one or two forms, binary crate. Crate is only at a time. Even if you run just C rather than cargo and pass a single source code file, as we did all the way back in the writing, the compiler considers that the file to be a crate. Crates can contain modules. Okay, makes sense. Okay. The crate root is a source file. Also they use a crate interchangeably with the general programming concept of a library. Interesting. Also the combine. The crate root is a source file that the Rust compiler starts from and makes up the root of module your crate. We will explain modules in depth in the defining modules to control scope and privacy section. The crate root is a source file that the Rust compiler starts from. The crate root is source file that Rust compiler makes up the root module of your crate. We will explain modules in depth in defining modules to control scope and privacy section. A package is a bundle of one or more crates that provides a section functionality. A package is a bundle of one or more crates that provides a set of functionality. One or more crates provides a set of functionality. A package contains a cargo.toml file that describes how to build those crates. Cargo is actually a package that contains the binary crate for the command line tool you've been using to build your code. Binary crate. It contains binary crate for the command line tool you've been using to build your code. The cargo package also contains a library crate that the binary crate depends on. Other projects can depend on the cargo library crate to use the same logic and cargo command line tool use. A package can contain as many binary crates as you like. A package can contain as many binary crates as you like. But at most only one library crate. A package must contain at least one crate. A package must contain at least one crate, whether that's a library or binary crate. Let's walk through what happens when we create a package. First, we enter the command cargo new. Cargo new my project. After we run cargo new, we use ls to see what cargo creates. In the project directory, there's a cargo.toml giving us a package. There's also src directory that contains main.rs. Open cargo.toml in your text editor and note there's no mention of src main.rs. Cargo follows a convention that src main.rs is the crate root of the binary crate with the same name as the package. Cargo follows a convention that src main.rs is the crate root of a binary crate with the same name as the package. Likewise, cargo knows that if the package directory contains src_lib.rs, the package contains a library crate with the same name as the package. And src_lib.rs is its crate root. Cargo passes the crate root files to rustc to build the library or binary. After we run cargo.new, we use ls to see cargo reads. Okay. There's also src. Okay, makes sense. Open cargo.toml in your text. Note that there's no mention of main.rs. Cargo follows a convention that src main.rs is the crate root of a binary crate with the same name as the package. Likewise, cargo knows that if the package directory contains src lib.rs. The package contains a library crate with the same name as the package. Crate with the same name as the package. The package contains a library crate with the same name as the package. And src lib.rs is its crate root. The package contains a library crate with the same name as the package. And src.lib.rs is its crate root. Cargo passes the crate root files to rustc. Cargo passes the crate root files to rustc to build the library binary. Here we have a package that only contains src main.rs. Meaning it only contains a binary crate named my project. If a package contains src main.rs and src lib.rs, if it has the two crates, a binary and a library, both with the same name as the package. A package can have multiple binary crates by placing files in the src bin directory. Each file will be a separate binary crate. Can have multiple binary crates by placing files in the src bin directory. Which is the correct order where A, B bins A contains B. How many packages does this package contains? 1, 2, 3, 4, 5. Shit. Main letters produces a binary crate, leave letters buyers library crate. Defining modules to control scope. Defining modules to control scope and privacy. Defining modules to control scope and privacy. Defining modules. Defining modules to control scope and privacy. In this section, we will talk about modules and other parts of the module system, namely passes that allow you to name items. The use keyword that brings a pass into a scope. Defining modules to control scope and privacy. Defining modules to control scope and privacy. In this section, we will talk about modules and other parts of the module system. Namely passes that allow you to name items. The use keyword that brings a pass into scope. And the pub keyword to make items public. We will also discuss the edge keyword, external packages, and the global operator. First, we are going to start with a list of rules for easy reference and you organizing your code in the future. Then we will explain each of the rules in detail. First, we will going to start with a list of rules. First, we are going to start with a list of rules. First, we are going to start with a list of rules. For easy reference, we are going to start with a list of rules for easy reference when you are organizing your code in the future. And we will explain each of the rules in detail. Modules cheat sheet. Here we provide a quick reference on how modules passes the user keyword. Here we provide a quick reference on how modules passes the user keyword and the pub keyword works in the compiler, and how both developers organize their code. We will be going through examples of each of these rules throughout this chapter, but this is a great place to refer to as a reminder of how modules work. How most developers organize their code. how most developers organize their code. We will be going through examples of each of these rules throughout this chapter, but this is a great place to refer to as a reminder of how this works. Start from the crate root. When compiling a crate, the compiler first looks in the crate root file. Usually src lib.rs for a library crate, for src/main.rs for a binary crate for code to compile. When compiling a crate, the compiler first looks in the crate root file. Usually lib.rs for a library crate, main.rs for a binary crate for code to compile. Lib.rs, main.rs for code to compile. When compiling a crate, the compiler first looks in the crate root file. Yes, usually or code. Okay. Declaring modules. In the crate root file, you can declare new modules. Declaring modules. In the crate root file, you can declare new modules. Say you declare a garden module with the mode garden. The compiler will look for the modules code in these places. In line, within curly brackets, replace the semicolon following mode garden in the file garden.rs in the file garden mode.rs. The compiler will look for the computer modules code in these places. Okay. In line. Within curly brackets that replace the semicolon following mode garden. In the file src the garden is in line within curly brackets that replace the semicolon following mode garden. In line with the curly brackets that replace the semicolon following the mode garden. Okay. Declaring submodules. In any file other than the crate root, you can declare submodules. For example, you might declare mode vegetables in src garden areas. The compiler will look for the submodules code within the directory named for the parent module in these places. In line, directly following mode vegetables within curly brackets instead of the semicolon in the file src garden vegetables rs. The file src garden vegetables module.rs. In any file other than crate root, you can declare submodules. For example, you might declare mode vegetables in src garden.rs. The compiler will look for the submodules code within the directory named for the parent module. The compiler will look for the submodules code. The compiler will look for the submodules code within the directory named for the parent module in these places. In line, directly following mode variable within curly brackets instead of semicolon. In the file src garden vegetables.rs and the garden vegetables.rs. Passes to code in modules. Passes to code in modules. Once a module is a part of your crate, you can refer to code in that module from anywhere else in the same crate, as long as the privacy rules allow, using the pass to the code. For example, an asparagus type in the garden vegetables module will be found at crate garden vegetable asparagus. Passes to code in modules. passes to code in modules. Once a module is part of your crate, you can refer to code in that module from anywhere else in the same crate. As long as the privacy rules allow. Using the pass to the code, for example, an Asperger's code type in the garden variables module would be found at create garden variables asparagus. Private versus public. Code within a module is private from its parent modules by default. Private versus public. Private versus public. Code within a module is private. Private versus public. Code within a module is private from its parent modules by default. To make a module public, declare it with the pub mode instead of mode. To make a module public, declare it with the pub mode instead of mode. To make items within a public module public as well, use pub before their declarations. The use keyword within a scope, the use keyword creates shortcuts to items to reduce repetition of long passes. In any scope that can refer to create garden variables asparagus, you can create a shortcut with use. Create garden variable asparagus, and from then on you only need to write asparagus to make use of the type in the scope. Here we create a binary crate named backyard that illustrates these rules. Here we create a binary crate named backyard. Backyard. Okay. The crates directory, also named backyard. Backyard contains these files and directories. It contains these files and directories. The crate root file in this case is src.main.rs, and it contains the file name src.main.rs, asparagus garden, mode garden. The pub mode garden line tells the compiler to include the code it finds in src-garden.rs, which is file name src-garden.rs. Pub mode variables. Here, pub mode variables means the code in src-garden's variables rs is included. 2. That code is derived debug pub struct asparagus. Now let's get into the details of these rules and demonstrate them in action. Derive debug pub struct asparagus. Now let's get into the details of these rules and demonstrate them in action. Now let's get into the details. Now let's get into the details of these rules and demonstrate them in action. Grouping related code in modules. Grouping related module in modules. Modules let us organize code within a crate. Modules let us organize code. Grouping related code in modules. Grouping related code. Grouping related code in modules. Grouping related code in modules. Modules let us organize code within a crate or for readability. Modules let us organize code within a crate for readability and easy reuse. Modules also allow us to control the privacy of items because code within a module is private by default. Private items are internal implementation details not available for outside use. We can choose to make modules and the items within them public, which exposes them, allow external code to use that and depend on them. As an example, let's write library crate that provides the functionality of a restaurant. We will define the signatures of functions but leave their bodies empty to concentrate on the organization of the code, rather than the implementation of a restaurant. In the restaurant industry, some parts of a restaurant are referred to as the front of house and others as the back of house. Front of house is where customers are. This encompasses where the host sits customers, servers take orders and payment, and bartenders make drinks. Back of house is where the chefs and cooks work in the kitchen. Dishwashers clean up, and managers do administrative work. An example, let's write library crate that provides functions of a restaurant. We will define the signatures of functions, but they leave their bodies empty to concentrate the organization of the code, rather than the implementation of a restaurant. Okay. To structure our crate in this way, we can organize each function into nested modules. To structure our crate in this way. Create a new library named restaurant by running cargo new restaurant lib, then enter the code listing 7-1 into src-lib.rs to define some modules and function signatures. Here's the front of house section. We define a module with mod keyword followed by the name of the module, in this case, front of house. We define a module with the mod keyword. We define a module with mod keyword. We define a module with the mod keyword followed by the name of the module, in this case front of house. The body of the module then goes inside the curly brackets. The body of the module then goes inside the curly brackets. Inside the modules, we can place other modules. As in this case, with the modules hosting, as in this case with the modules hosting and serving. Modules can also hold definitions for other items, such as structs, enums, contains, traits, and as in listing 7-1 functions. Modules can also hold definitions for other items. 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 Modules can also hold definitions for other items, such as structures, enums, constants, traits, and as in listing 7-1 functions. Modules can also hold definitions for other items. Modules can also hold definitions for other items. Modules can also hold definitions for other items. Such as structures, enums, constants, traits, and sig. By using modules, we can group related definitions together. By using modules, we can group related definitions together and name why they are related. Programmers using this code can navigate the code based on the groups rather than having to read through all the definitions. By using modules, we can group related definitions together and name why they are related. Programmers using this code can navigate By using modules, we can group related definitions together and name why they are related. By using modules, we can group together and name why they are related. Programmers using this code can navigate the code based on the groups rather than having to read through all the definitions, making it easier to find definitions relevant to them. Programmers adding new functionality to this code should know where to place the code to keep the program organized. Earlier, we mentioned that src email address and src lib address are called create roots. The reason for their name is that the contents of either of these two files from a module named create at the root of create's module structure known as the module tree. Listing 7-2 shows the module tree for the structure in listing 7-1. Listing 7-2 shows the module tree for the structure. Listing 7-2 shows the module tree for the structure in listing 7-1. Listing 7-2 shows the module tree for the structure in listing 7-1. Listing 7-2 shows the module tree for the structure in listing 7-1. Listing 7-2 shows the module tree for the structure. 1. Create, front of house, hosting, serving, add to waitlist. Add it to waitlist is yes, makes sense. This tree shows how some of modules nested inside one another. For example, hosting nests inside the front of a house. The tree also shows that some modules are siblings to each other, meaning they are defined in the same module. Hosting and serving are siblings defined within front of a house. If module A is contained inside module B, we say that module A is the child of module B, and that module B is a parent of module A. Notice that the entire module tree is rooted under the implicit module named create. The module tree might remind you of the file system's directory tree on your computer. This is a very apt comparison. The module tree might remind. Second, what? This tree shows how some of the modules nested. Okay, makes sense. Hosting nests inside the module of the tree also shows that some modules are siblings to each other, meaning they are defined in the same module. The hosting and serving are siblings defined within front of house. If module A is contained inside module B, we say module A is the child of module B. B is the parent of module A. Notice that the create entire module tree is rooted under the implicit module named create. Notice that entire module tree is rooted under the implicit module named create. The module tree might remind you of the file system directory tree on your computer. This is a very APT comparison. Just like a directories in a file system, you use modules to organize your code. And just like files in a directory, we need a way to find our modules. The module tree might remind you of the file system's directory tree on your computer. This is a very APT comparison, just like directories in a file system. You use your modules to organize your code, and just like files in a directory, we need a way to find our modules. You use your modules to organize your code. This is a very APT comparison, just like a directories in a file system. You use your modules to organize your code. You use modules to organize your code. And just like files in a directory, we need a way to find our modules. Which is of the following is not a good reason to use a module? Modules boost the runtime performance and independence of the code within the same module. Modules group-related code programmers can also modules group-related code, so programmers can more easily work in a large code base. Modules encapsulate implementation details that shouldn't be used by external clients. Modules provide a scope to avoid naming conflicts across part of the code base. Modules encapsulate implemented details that shouldn't be used. Modules revealed. Yep.